machin, je sais pas si vous allez bien, moi ça va. Donc, okay, we'll go back to English now. I've decided to split this into the AS first and a separate video to the A level. So, those who want the A level film as Scorpio, I'm going to put that in a separate video. So I'm going to put the AS first, which is what I'm going to do right now. And have a full A level content, which will have the AS at the beginning, and then the full A level following it in the rest of the video. So, yeah, just thought I'd let you know.
Alright, so in this video, I'm going to go through everything that you need to memorise for your core pure maths exams for further maths at A level. Okay. Now, we'll start with complex numbers for core pure 1. We'll do the AS first, and we'll move on to core pure 2, which are usually all the second year stuff, such as hyperbolic functions, etc. Okay, so Cartesian form of a complex number. Z equals x plus iy. Always that form, we always remember it. I like to put a little line through my Z just so it doesn't look like a 2. Mod argument form. Z equals r times cos theta plus I sine theta. We should know that. What are the conjugates? Well, they come in pairs. Or should I say roots come in pairs? That means if I have Z is x plus iy, Z star, which is the conjugate, is x minus iy. So we just change the sign there. If I'm rationalising or realising the denominator, so I've got things like 3 over 2 plus 4i. If I want to go ahead and realise this, I will multiply by the conjugate. So I will multiply by 2 minus 4i and 2 minus 4i. Top and bottom, what I do there. Multiplying, if I'm multiplying, be careful what I do to the moduluses. If I multiply the mod and add the arguments, or if I'm dividing, I divide the mod and subtract the arguments. Now, the multiplication of the argument form is when I've got things like cos theta minus I sine theta. Now, the best way to deal with that is to write it as cos of minus theta plus I sine minus theta. That's the easiest way to get around it. That's your basic complex number theory for core pure 1. Alright. So, now we're looking at the Argand diagram and the loci. So, loci in an Argand diagram, if I've got z minus z1 is equal to z minus z2. What this is, as you should know, is a perpendicular bisector. What that means, if I have something like that, of z1 and z2, the perpendicular bisector was something that cuts at it like that. That's perpendicular bisector. This, z minus z1, the modulus of that is equal to r. Well, this is a circle. Radius r at centre is z1. If it was z plus z1, you have to do z minus open bracket z1, and then you take the minus of that when you have to manipulate these a little bit. The argument with z minus z1 is equal to theta. Well, this is the half line. This is the one that people find confusing when they're intersecting. The argument with z minus z1 is equal to theta. Well, it's at angle theta at z1, the positive of z1. We take this bit as the positive bit there. So make sure we change the sign for that one and we change the sign for that one. If they were positives, you would have to multiply them. Okay? So if I had an example of z minus 3 modulus is equal to 4, what this will be, this will be a circle, radius 4, centre of 3, 0. Right. So I'm literally just moving this along on the axis. So that is your loci in your Argand diagram. Alright, so now we're looking at the series. So the sum of results, the sum from r is 1 to n of k, Well, that is k times x. That's a relatively simple one. Sum from R1 to n of r. Well, this is the Gauss formula. This is a half nm plus 1. The sum for the r squareds is a sixth n plus 1 2n plus 1. How you remember that one is up to you. And this last one here for r cubed is a quarter n squared n plus 1, I think. You can tell me if I got it wrong. The more important bit is if we're starting at like r is 2 or r is 3 or r is 4, something like that. So if I've got the sum from r is some number k to n of r, what I do is I do the sum from r equals k to whatever number minus the sum from r equals 1. Rather, I should put that's the 1 bit. 2. And it goes up to k take away 1. So we do whatever 1 less is than what we started with. So really, you do 1 less than what you go up to, because then that will give you the middle terms essentially. So we're taking all the ones up and we're taking the ones away. It's a bit like with areas in integration when you've got, I want to go from one limit from 0 to 4, but then I want to go between 2 and 4, so I'll go between 0 and 2 again. If that makes any sense. If it doesn't, leave me a comment and I'll try and explain it in a better way than what I have to describe. There you go. Series. Alright, so now volumes of revolution. We've got a volume of revolution around the x-axis in Cartesian form will be pi times the integral as around the x-axis, so it's y squared dx. Whatever it's in respect to is also what it's going around. And these limits are x values. Okay. For y-axis, it's pi. Well, it's the inverse of this. Of 2 y values, and those 2 of x squared dy. Now, for a cylinder and a cone, these are the 3D solids that you should know. So for a cylinder, it's just pi r squared h, and for a cone, it's 1/3 pi r squared h. This is not IS material, but I might as well put it in here while I'm doing it. The parametric forms, so for around the x-axis, it will be pi times the integral between those 2x values of y squared dx by dt. For the y-axis, you could probably guess what the other ones will be. It's pi times the integral of x squared dy by dt. Because these are in the forms of the parametric integration stuff that you should know from single level maths. Well, for an Excel, this was only added late, parametric integration, but you should be aware of it because it can come up again and again and again, and it's just nice to be aware of it if it does come up. Parametric volumes of revolution are used when you cannot eliminate t variable in parametric equations. So if you've got like t x squared plus 1 and tx squared plus 3, for example, I don't really want to be equivalating them and doing a lot of mess with them. There's no really any point of doing that. So you might as well just use the parametric forms that are given. Alright, that is all you need to memorise for volumes of revolution. Okay, so with proof by induction, we need to realise these 4 steps. The base case we always check is n equals 1. That's the bog standard, it's really easy. The assumption is that n is equal to k. The inductive step is where you have to do some work. Is n equals k plus 1. If it's proving divisibility, you do f of k plus 1 minus f of k. The conclusion step, since true for n equals 1, and if true for n equals k, also true for n equals k plus 1 by induction, true for all n belonging to the positive integers. That's just a form I did get learning and then just write it out whenever you need to. That's basically what you need for your conclusion for proof by induction. Okay, so next we're going to have a look at matrices. So if we're going to look at the non-commutativity of matrices, what that means is that A multiplied by B is not equal to B multiplied by A. Whereas with normal numbers, AB is typically BA the other way around. A 2 times 3 is the same as 3 times 2. Like that. The associativity of matrices, however, is slightly different. Like if I do A, B, C, I can do them in any order. I can A, B times C would therefore be equal to A times matrix BC. That's what I mean by the associativity. Now, for an identity matrix, if I take A and I multiply A by the identity, I get IA back. And you'll see when I multiply the inverse by itself, I get back the identity, and so forth. So that is the basics of matrices. Now we're looking at the main bulk of chapter 6 now on the inverse of matrices. So the basic definition of an inverse of a matrix, we should know that A multiplied by A minus 1 will give us the identity back. Basic stuff, which is the same as doing A minus 1 times A. It doesn't matter which order you do them. Products of inverses, well that's AB inverse is B minus 1 A minus 1, not the other way around, just got to be careful. If I want the determinant of a 2 by 2 matrix of A, B, C, D, I do A, D minus B, C, make sure it's a minus in the middle. For a 3 by 3, A, B, C, D, E, F, G, H, I want A lots of the determinant, crossing those two out, of F, E, F, H, I, plus B minus B lots of the determinant of D, F, G, I, and then plus C lots of the determinant of D, H, and E, and G. Now, a 2 by 2 inverse of a matrix is what you do. For A inverse, you do 1 over the determinant, and you will multiply that by, gotta remember the right way around now, it's you swap those and you minus those. That's what you do. You swap the diagonal and you minus the other two. Simple enough. For a 3 by 3 A inverse will be 1 over the determinant of the matrix times the matrix transpose. So where every row comes every column and every next row comes every other column, and so on and so forth. And the last bit, a self-inverse matrix, it is if A is equal to its inverse. That's what I mean by self-inverse matrix. And that is the basics of matrix inverses. Okay, so the next bit with matrices is looking at systems of equations. Okay, so the first thing we do, step number 1, is we check the determinant of the matrix. That's step 1. If my determinant of my matrix is not 0, that's important because that tells us that the planes meet at a single point. That's the first bit. The next bit is, well, if the determinant wasn't 0. Right? Well, if the determinant is equal to 0, what's the next thing we should do? Well, we check consistency. Now, there's 2 ways this can go. If this is consistent, our solutions, i.e. the solutions exist. So it could be, for example, a sheaf. A sheaf is kind of like them all intersecting with each other, or it could just be that they're in the same plane, depending on where they are. That's quite useful because you can spot, well, we've all got multiples of each other, so therefore must be in the same plane. Well, they're all going to meet at one point on the same plane, right? Otherwise, from here, it could just be, well, it could just be inconsistent, which means aren't solutions. Or there are, but there's infinitely many of them. So, from here, we check parallel. We're checking the parallel planes. It could either be 2/3 are parallel, which more often is the case. 2 or 3 are parallel to each other, so basically parallel them with each other in a line. I can't really draw that on the board, but it's like that one, and that one, and that one. They're all going in the same way, in the same direction. Or it could just be there are no parallel planes. And if there are no parallel planes, well, we form a prism. Nice and easy. That's where the other one comes in, the prism. Alright. So when I'm doing a matrices system of equations question, that's what I want to be doing. That's my little thought process, getting the order right. That's most important here. Can you follow this order when you're doing a system of equation matrix problem? The next bit is bits on vectors, which is going to be the longest part of this video. That's next. Sort of lied a bit. The next bit actually is on linear transformations, which I completely forgot. It's not in the textbook that much. But an invariant point in general for some xy's, if I multiply the matrix by xy, I'm going to get that same point back. That's the more important one. This one, these next two, they don't really come up in the textbook that much, but they're in there. If I take the matrix and multiply it by some x and some ax, when I got y being ax using this general one, if I manipulate that just a little bit, then I've got some multiple k of x and ax. That is the fundamental one for ax when it's going through the origin. This one, it doesn't come through the origin. Now, it's quite sneaky, these questions, because, well, I've never seen actually one come up yet. But we have m times x, mx plus c. Okay, where there's two different m's, capital M and lowercase, that makes sure it's different, is equal to x dash mx dash plus c. That does not mean derivatives. All that means is some other point on the line. It goes back one and then moves to it, if that makes any sense. So it's any point that maps to it from another point, if that makes any sense. The area scale factor, well, the determinant of the matrix is equal to the scale factor. Successive transformation, so the transformation PQ is QP. It does the other way around, make sure you remember that. And the rotation of theta degrees anti-clockwise, well, that's a matrix of cos theta minus sine theta cos theta. Remember, it's anti-clockwise, so if it's going in a clockwise direction, make sure you actually check and make sure you go the other way around when you're actually working through. And make sure you read the question carefully, because it only works for anti-clockwise, that little matrix there. So, that is a few more bits for linear transformations. So the final bit on linear transformations is a reflection any plane in x is 0, y is 0, or z is 0 has each of these. Whichever one it's in is whichever one the one is negated. So that's an easy way to determine which one is which. For rotation about the x-axis anti-clockwise, we remember we're putting that little formula that we had in 2 dimensions, or just in 3 dimensions. Doesn't change that one. This is the one that I'm going to put a little star next to, because this one changes a lot. We would expect the negative to be in the top right. However, with the y-axis, this one is negated at the bottom left. That's the only difference between this one, which is why I'm going to put a star next to it. The z-axis just stays like the axis, cos theta minus sine theta cos theta. That one doesn't change. It's only the one about the y-axis, which you need to be careful of, because it's the bottom left that's negated, not the top right. That's what we need to know about linear transformations though. Okay, so now we're on to this huge topic of vectors, chapter 9 in the Excel book. We need to know our definitions for certain vectors before we can get cracking. starting with the scalar dot product. Now you have to be careful with the scalar dot product because it is the modulus of A times the modulus of B times cos theta. And we have to be careful where we find our angle, because our angle has to be, that's vector A, that's vector V. Your angles must be away from each other, forming this angle that you're going to make at the bottom. So you need to be careful of that. A dotted with B is equal to 0 if A and B are perpendicular. Vector line equation, I mean, some bog standard stuff into here really. It's A plus lambda B, where A is the position vector and B is the direction vector, telling you which direction the line is going in. This one, I've just wrote that from the formula book, that x minus a1 over b1 is equal to y minus a2 over b2 is equal to y minus z minus a3 over b3 z, which is all equal to lambda. That is if you're converting from a vector line into a Cartesian or vice versa. The parametric line equation from the formula book, I wanted to write this one out so you actually remember it. It's a bit like the line, it's a plus lambda b plus mu c. Make sure you underline all your vectors in the book. The scalar product plane equation is r dotted with the normal vector, and your normal is usually n hat, will be equal to a dotted with a normal vector. Alright? And a dotted with a normal will just give you some constant, you can call it d if you wish. The last one here at the bottom is also in the formula booklet. I will write down the formula booklet side here. It's also in the formula booklet, but again I won't bother remembering it. n1, n2, n3 are the coefficients of your normal vector. So you're going to multiply them by your x, y and z, and you're going to get it equal to some number at the end. Make sure when you're sticking it in that you do it correctly. Okay? So this is your box standard vector knowledge. So now we've got that basic vectors knowledge, we can now look at angles between two vectors. Now we've mentioned the scalar product already, but we need to rearrange that scalar product into a more useful form. So we have the scalar product with A dotted with B, mod A, mod B, mod B. So for the angles between two lines, what you do is you take A1 dotted with A2 and you divide it by the two moduli of A1 and A2. Okay? Bog standard, nice and easy. And to make sure you take the modulus of each if you want the acute angle and not take 180 miles away from the other when you get an obtuse angle. Because that will just give the obtuse, but when you take the modulus of the whole thing, you'll get the acute angle, which is what you want. The angles between two planes are a little bit more sneaky. You take the normal of one and dot it with the normal of the other, and divide it by each modulus of the two normal vectors. Nice and simple. So you dot the two normals and you divide them by the modulus of each two multiplied together. For a point on a plane, you need to be slightly careful. You do A1 dotted with the normal vector over the modulus of A1 times the modulus of the normal. That's the hardest one to remember, I think, the points on the plane. Now, the next bits are looking at the intersections, shortest distances, and any reflections in reflecting a point in a plane or reflecting perhaps a line in a plane, which is probably one of the hardest questions you could ever get in terms of vectors. So that's what's coming next. Alright, so now I want to look at the intersections of vectors. Now, for intersections between two lines, you equate R1 to R2, you find lambda and mu from each equation of lines. Then they either intersect, they're parallel to each other, or they're skew. Now, which one's which? Because people get confused between these two. This top one here is skew because they don't intersect and they're not parallel. This one here obviously is parallel lines, we know what parallel lines look like. And here they intersect at one point. Nice and easy. For a line of plane, it must be in the scalar product form. That's what it's fill in there. If they're not in the scalar product form, you can't do anything with them. and you're going to sub the line into the r dot n equals d equation of the form, because you will find whatever this normal vector is here to the plane, and you'll have it all in that form already, and you can just go with it. It's nice and super simple. When we're looking at two planes though, we need to be slightly careful, because we're going to take 2 points that are on both of these planes, like here and here for example. Those 2 points there will be completely fine. We're going to find a line through them in vector form, and then you're going to let either n be 0 or 1, and you're going to solve for x and y simultaneously to find where they intersect. The 2 planes will intersect each other. Some nice, simple questions there for intersections of vectors. Next, shortest distances. The last bit that I'm pretty much just going to talk through here is the vectors with shortest distances, or what's usually called perpendicular distances. So for a point in a line, we're going to find a vector between a point that we know and a general point on the line, and we're going to make this perpendicular to the line direction here, not the position vector of the line. For parallels, we want to find the vector between 2 general points. Then we're going to let the substitution that t is lambda minus mu, take one away from the other, and we're going to make that perpendicular to line direction as before. Nice and simple. Parallels like that, and that's your point on the line there. For skew lines, we're going to find a vector between 2 general points on the lines, here and here, and we're going to make those perpendicular to both directions. The both is the important bit there, and then you're going to solve those simultaneously with 2 equations with x and y. Yeah, pretty simple. This one here for a point in a plane, this is the one that usually comes up. It's in the formula book, which the distance is m1 times alpha plus n2 beta plus n3 gamma plus d. Take the modulus of that divided by the length of the normal vector will give you the shortest distance between the point, a general point, and the plane, which is given in the standard parametric plane form, or Cartesian plane form rather. For 2 parallel planes, we're going to find any point we possibly can on one of the planes, it doesn't really matter which. And from there, we're going to use that formula, nice and simple, because we've just got 1 point now, and we can just get it to one of the planes, and then we're away pretty much from there. Just to explain what I was doing there, if I take a plane, I can say any point I wanted on that plane, and it's the distance there from the point to the plane. It's the intersection of the plane that's the most important bit. If I can't really draw a plane. If I draw 2 planes like that, and you want the shortest distance between those 2 planes, that's what's visually going on here. I like drawing these diagrams because it visually shows what's actually happening when you're just looking at them, because you just learn these methods and then you don't actually get told what's actually happening. Well, if I draw the diagrams, it actually makes more sense to what's happening. So the last bit is what I consider the hardest bit, which is reflections of vectors and points in vectors. Let's go in next. Okay, so this is my last bit now for Tokyo 1 and we're finished. For vectors and reflections of vectors, like for example a point in a plane or a line in a plane, this is what we do. So for a point in a plane, just as I've drawn in my diagram, we find the intersection of the normal through the point in the plane. This is reasonably simple. I'm going to add that vector that we've got onto the point of intersection that we found, which essentially will flip it, flip the point in the plane, i.e. reflecting it. For a line plane, this is what I consider the most hardest thing in Tokyo 1 vectors, and we're going to reflect the point as above that we've done there. We're going to find where the line that we've got intersects the plane, which is not so bad to do. And we're going to find the equation of the line through the point of intersection that we've found here, and the reflected point. So we're going to get those 2 there, which in a sense will do what's happening over here. I've got the point that I want to reflect. I will reflect the point as I've done before. Reasonably simple. We'll find where that line will intersect the plane itself, and then we'll find the equation of the line through the point of intersection, which is through there, and then we'll reflect that point over, eventually giving you the point that you would want, and you're reflecting that entire line. That's Tokyo 1 for you. Next